Okay. So let's take a look here. We're gonna jump, like I said, we'll do another example that's kind of like not with slant asymptotes. Then we'll do a little side trip to the slant asymptotes, and then we'll see one with the slant asymptote too. So again, graph the function is our direction. Are the directions here? F of x equals 3x squared over x squared minus 4. Okay, so we'll go through all the little pieces here like we have in the past, right? So for example, we'll identify the domain. Okay. And so do we have any numbers that we need to restrict from our domain in this problem? Or do we have any possible domain restrictions? So for example, could we take the square root of a negative in this problem? No, so we don't have to worry about imaginary numbers or restricting those. Could we divide by 0 in this problem? Yes. So we're going to take that x squared minus 4, set it equal to 0 to kind of figure out what x values are going to give us 0. You could factor here if you wanted to make it x minus 2, x plus 2. I'm just going to add the 4 over and then square root both sides. And so we end up with then x is plus or minus 2, right? That way works as well. All right, so our domain then is going to be negative infinity to negative 2 union negative 2 to 2, good. And then 2 to infinity. All right, so there is our domain. Please be careful, right? When you have those two domain restrictions, don't forget the middle interval there, okay? Some students take it from negative infinity to negative 2, and then they go right from 2 to infinity, and they don't think, oh, right, there's numbers between negative 2 and 2 that would still work. Okay, question?
Would you take points off if we don't put the U or anything in?
Nah, not really, but I mean, technically it should be there, but nah.
Okay.
Nah. All right, so those domain restrictions, right, they're going to be either holes or vertical asymptotes. So how can we check to see which one is which or what they are? What are we looking for? For vertical asymptotes, it's when the function will be what? Divide by a 0, right? Undefined. Undefined is what we're looking for. Something over 0, right? So something over 0. Whereas a whole, we're looking for something that gives us 0 over 0. Okay. Both 2 and negative 2, they are undefined in this case, right? If I plug a 2 or negative 2 in here, we get 0 in the denominator, but we get a number in the numerator. And so both of these are vertical asymptotes. So 2 vertical asymptotes. Okay. Are we going to have any holes then? No, there are none. Okay. Our two domain restrictions, the two places where our denominator equals 0 are accounted for. They're vertical asymptotes. There's no other candidates left over for a 0 in the denominator there, so we can't get 0 over 0. There are no holes. Do we have any zeros or X-intercepts here? Okay, well, a 0 occurs, right, when we have the coordinate x comma 0, right? So we want to know when our y coordinate is 0. In other words, when our function is 0. Well, right, 0, 0, right? A function or a rational function can only ever equal 0 when the numerator is equal to 0. 3x squared equals 0 when x is 0. So you get the point 0, 0. 4 times 0. All right. Do we have any horizontal asymptotes here? Well, how do we find a horizontal asymptote? Yep, we're going to use the limit is x approaches infinity and then like our degrees and stuff like that. Okay. Okay. So, what will this limit approach here? 3. Exactly right. Okay. Numerator over denominator there, 3. And so the equation here will be y equals 3 for that horizontal asymptote. Okay, so I'm going to go, I'll leave some space here for us to find additional points if necessary. Okay, so I'll just add points. And then we'll go ahead and just get this thing graphed. So let's see here. Vertical asymptote at 2, negative 2, 0, 0, 0. So I'm going to maybe, oh, actually, I know what it's going to look like. So I'm going to go ahead. sketch it this way. Hopefully that'll be enough there. We'll see. All right. Oops, I'm off the screen. There we go. All right, so I'm going to plot our vertical asymptotes here at 2. I'll use a different color now that I'm graphing. And vertical asymptote at -2 as well. And horizontal asymptote at 3. No holes to plot, but we do have the 0 at 0, 0. So I'm going to plot that 0, 0. There's a point. That's all we've got. And we're supposed to kind of figure out what this graph looks like based off of this. So, little strange here. Okay. So I think we need to come up with some additional points. All right, I think we should probably come up with some additional points here. So, for example, let's try, well, I want to figure out what's going on between the two asymptotes maybe first. You can kind of do whatever you want as far as where you start, but I'm going to start between the two asymptotes here. So I'm going to try like -1. Let's see what f of -1 gives us. Okay. So f of -1, let's see, we're going to get 3 in the numerator times -1 squared, and then -1 squared minus 4. So we get 3 over -3 or -1. Okay, so we get the point -1, -1. Plot that right there. Let's also try +1, f of 1. So it's going to be 3 times 1 squared over 1 squared minus 4. If you want to just do this mentally too, feel free. I'm just writing out the notes and stuff like that. Okay. We get 3 over -3, which is also -1. So we get 1, -1 as well. Okay. And so what kind of shape does it look like we're maybe making here? Probably like a parabola, but of course parabolas don't have like, parabolas don't approach asymptotes, right? I mean, they do have like end behavior that goes to infinity, but a parabola wouldn't have like an asymptote that's approaching there. So I'm not sure if we could actually like, I don't know if we could technically call this thing a parabola. Maybe we can. I'm not sure. That's a question I'm not sure about. But anyway, we know it's going to kind of have that shape at least, where it's going to kind of come up and go down like that and approach those asymptotes like that. Okay, so that's our piece. Okay. Is that it, right? Maybe there's more, so we should probably pick some other points here. What might be another good point to pick to kind of see if there's more to the graph or something like that? What's another good x value to pick here? 5, 3, 4. Yeah, anything over here beyond this x value of 2. Okay, just in the hopes or in the interest of trying to keep the numbers a little bit, hopefully, nice to work with here. In the interest of trying to keep the numbers a little bit nice to work with, I'm going to do like 3. Hopefully it's going to keep the numbers small enough to make it easy to calculate. So 3 times 3 squared over 3 squared minus 4. And so, goodness, 27. Well, hopefully this is going to be okay. 9 minus 4 is 5. So 27 fifths, which is 5 and 0.4. 2 fifths, so 0.4 then? Yeah? Okay. So 3 comma 5.4. That's not too bad. So 1, 2, 3, 1, 2, 3, 4, 5, 0.4. So it's like not quite a half. So something like that. Okay. And I think at this point we kind of have an idea about what's going to happen, right? I mean, you can get more points if you want to, like use 4 or 5. But I think we can kind of see here we have this vertical asymptote, so certainly got to come down from there, and then we'll just kind of approach that horizontal asymptote like so. Okay. And then I'll try -3, 2. just because, and I'll just do this one here mentally. So we're going to get 27 in the numerator over 5 in the denominator again. So we're going to get 5.4. Okay. So negative 1, 2, 3, and then 3, 4, 5, and a little bit. So okay, something like that. Okay, not quite your typical rational function there, but I mean it is. Yeah, that's what it looked like, something like that. So you can see there's some symmetry. Right, that's helpful too in this case, but anyway, I didn't quite put those points in the same spot, but close enough. All right. Questions? Oh, yes, Megan and then Riley.
Are we gonna have cases where like the function goes below the horizontal asymptote before reaching the end behavior?
So that's a good question. I don't think that's something you'll need to worry about for these. No, and like in the future mathematical career, yeah, you're going to see that happen. But for right now, I would say, and like not that you're going to need to like sketch the graphs of those. I mean, you'll see it show up, but I don't think now. I keep it pretty much that the horizontal asymptotes on all approach and stuff like that, because otherwise it's just more to keep track of and stuff like that. I mean, I guess you could. An easy way to see if your graph is going to cross the horizontal asymptote. Do you guys have an idea about how you can figure that out? How can we figure out if our graph crosses the horizontal asymptote or not, if it's going to go beyond it? So, yeah, Mark? What's that?
If like zeros, because it goes, in this case, you'd have to cross an axis maybe sometime.
Okay, so it's going to cross, right, but we're not sure, in this case, our horizontal asymptote is at 3, so it's not, we don't want to set it equal to 0. We're okay if it crosses the x-axis. We just want it to cross 3, so we'll set it not equal to 0, we'll set it equal to 3. And so if you take that, okay, and so we'll set 3, which is our horizontal asymptote here, equal to our function, cross multiply, so we get 3x squared minus 12, or that's multiply both sides by x squared minus 4. Okay, so the 3 will distribute there to be 3x squared minus 12 equals 3x squared. Okay, subtract 3x squared from both sides, what are we left with? Yeah, negative 12 equals 0, which, what does that mean? It's not true, so there are no places, so you don't have to worry about the graph crossing the horizontal asymptote. You know it's not going to. Okay, now granted, will I ask you to do something, like will I ask you to like really do that calculation? Nah, it's okay kind of thing. But we will be able to, at least we can use that to at least see, will it cross? And if so, then we'll know kind of, a better picture. But all of ours should be safe. So it's relatively easy to tell if you're going to cross or not. So, all right, any other questions? Riley, you had a question.
Are you going to want us to find y-intercepts at all?
If you want to, yes, but not necessary. No, not necessary. You should be able to if I ask, I guess, kind of thing. If it's asked, what's the y-intercept of this thing? Which is easy enough. You just plug 0 in for x and find the y value. But I won't make it as, it's not part of this, no. And I'm not sure why I don't do it. I just don't. Yeah, I could though, for sure. All right, so that's a rational function, a little bit more of a strange one. But what I want to jump into now here is talking about slant asymptotes, just briefly introduce it, and then we'll do a problem with slant asymptotes, and then I'll just cut you loose on the homework, okay? But we'll talk a little bit here about slant asymptotes and then do an example. Okay. So asymptotes don't have to be vertical or horizontal. They can also be diagonal, I guess. A slant asymptote occurs, or these occur, when the degree, we talked about this yesterday, I think, right? The degree of the numerator is 1 greater than the degree of the denominator. Okay, if the degree of the numerator is 1 greater than the degree of the denominator. Okay. And so what we're going to do here, as an example, is we're going to identify the equation of the slant asymptote. Okay, if it exists. Because that definition of the slant asymptote, or like I guess how we know when it occurs, that only tells us how it occurs, right? We wouldn't be able to graph that because it's like, well, okay, we know there's one, but how do we graph it, right? We need the equation for the line, the slant asymptote. So you need like a slope and intercept and stuff like that. Well, let's get this example function here. X squared plus 1 all over x minus 1. Okay. Will we have a slant asymptote here? Yes, the degree of the numerator is exactly 1 more than the degree of the denominator. Okay. To find that slant asymptote, we're going to do long division. Okay, so x minus 1 goes outside my little division symbol there. And then what's going to go inside the symbol? X squared plus 0x. Very good. Plus 1. Okay, don't forget those placeholders. Cooper, question? Alternatively, we could use synthetic division. Cooper, what would that look like?
The box with 1 in it.
1.
And then 1 plus 1. And
So,
1.
say again. 1,
And 1.
1 and 1, like this?
Except, no, 1, 0, 1.
Don't forget the placeholder. 1, 0, 1. Okay, don't forget that placeholder. All right? That's okay, Cooper. You were just trying to help out the other people that maybe would have forgotten it too. Because otherwise, if you get it right all the time, other people might, I don't know, they might not understand why, certain things are wrong. So thank you for pointing that out. Okay? So let's do it either way you prefer here. I will use long division because... Okay, so those cancel. Left with 1. Bring down 1x, I should say. Ooh, forgot the x there. Okay. And then 1x plus 1. So let's see, it's going to be a plus 1. 1 times x is 1x. 1 times minus 1 is minus 1 minus that. Plus the opposite. Those cancel. And we get 2. Oh, we get a remainder. Okay. So a remainder would be plus 2 over, the x minus 1 here, right? That would be the answer to the long division. Over here... Okay, so x plus 1 plus the 2 over the x minus 1 kind of thing. Okay. So in each case, right, we get a remainder of 2, or, if we put it into our function there, 2 over x minus 1. The equation for the slant asymptote is what you get when you throw out the remainder. Okay, so throw out the remainder, x plus 1, that is the equation for the slant asymptote. Okay, that's all there is to it. Y equals x plus 1. Okay. Yes. Thank you. All right, so I'll give you guys one to try here. I think you get the point. So here, you guys try this one. F of x equals 2x squared minus 5x plus 7 all over x minus 2.
Can you slide it a little bit?
Yes. I'll zoom it out just a little bit. There we go. So go ahead and try that one. Come up with the equation for that slant asymptote if one exists. You might want to determine whether one exists first and then go from there. Oh. All right, what's the equation of the slant asymptote? 2x minus 1, exactly right. Okay? So there is a slant asymptote there. All right, questions on any of that? All right, yes, Megan.
What would you do if the degree was greater than 1 more, the numerator and the denominator?
Yeah, so you're saying like if it was like, if this was like x cubed and this stayed x minus 2 or something like that? So that is a good question. Let me look at that because I feel like I looked at this before. So let's try that. So we'll just make it 2x to the third instead. Minus 5x plus 7 divided by x minus 2. Interesting. Okay, so here's what the graph of that would look like, again, with the 2x to the, if we made that 2x to the third. So let me just write that down here. So looking at 2x to the third, minus 5x plus 7 now over x minus 2. Okay, it looks like, well, if we do that with like the synthetic division too, let's just see, maybe we can figure something out with that. So let's be 2, 0, negative 5, 7. I almost put another 0 in there. All right, 2, 4, 4, 8, 3, 6, and then 13. We're going to throw that out. So it looks like 2x squared plus 4x plus 3. So maybe is there like a quadratic asymptote or something like that, right? So let's see if I graph that alongside it. So 2x squared plus 4x plus 3. And if you didn't, I'll graph it like thicker, I guess, which might be too much, but we'll see. You kind of see, I mean, this does kind of approach the behavior here, but then it doesn't really do anything much down there. So I don't know, there is some kind of like vertical asymptote kind of feel to it there. I'm not sure if that makes any difference or not, but I don't know. Yeah, that's a good question. I'm not sure. But there is, it looks like there is something to it at least. There is something. Okay. That being said, though, and I guess, well, I wonder if I should have graphed in the, because we also have a vertical asymptote at 2, so that might have been, yeah, interesting. Well, you can also see the vertical asymptote there at 2 as well, that kind of asymptotic behavior approaching there. So, I don't know. But I do have one more graph then for us to try here. Something that's more simple, where it's just differed by a degree. So, nothing quite so interesting as a quadratic asymptote. Graph the function f of x equals x squared minus x plus 1 all over x minus 1. Okay. So I'm going to give this for some of you guys to do right now. So go ahead, you guys identify the domain. Give me any vertical asymptotes if they exist. Give me any holes if they exist. All right. And then identify any zeros if there's any zeros. And then for number 5, so now here's an interesting point, right? So are we going to have a slant asymptote in this problem? Yes, and we know that because the degree on the top is 1 greater than the degree of the bottom. Okay, now normally on step 5, I'm asking you to find horizontal asymptotes too. Are we going to have a horizontal asymptote in this case? Why not? Well, right, so it's either one or the other, right? In order to find horizontal asymptotes, we take the limit as x approaches infinity. But as x approaches infinity here, right, our numerator has the bigger degree than the denominator, and so that means the limit wouldn't exist, okay? But that's the exact condition we're going to need to find a slant asymptote. So like Ryan said, right, you're going to have one or the other. You won't have both a horizontal asymptote and a slant asymptote because of the degree stuff, okay? So one or the other. So in this case, slant asymptote. So you can go ahead and find that one. Okay. And then if you need, well, we'll see if we need any additional points too. Okay. So go ahead, take a few minutes there and just answer those questions as best you can. I will do the same. like where the curve is actually going to go, but you got the bonus part of that. So. Okay, so I guess I'll zoom out a little bit more. Let's see, can I do it? Yeah, okay, something like that. Say again? Yeah, sure. Well, I'm not quite done yet. Okay, so I've got my vertical asymptote in there at x equals 1. Got my slant asymptote in there at y equals x. Okay. We have no zeros, right? If you try and set your function equal to 0, which is really when the numerator equals 0, excuse me, x squared minus x plus 1 equal to 0. Well, it doesn't factor, but that doesn't mean there's no answers. Just because it doesn't factor, right, we could check, or we must check the quadratic formula. But unfortunately, when you use the quadratic formula there, you're going to end up with, well, your discriminant will be imaginary, right? Or your discriminant's negative, or square root of negative is going to be imaginary. So we won't count that, right, because we're not graphing on the imaginary plane here. We're real numbers. Okay. Doing the long division or the synthetic division there gives us our slant asymptote. So we have no points. We have these boundaries, but we have no points. So what might be a good point to pick here? X equal to what?
3.
Okay, 3 or 2, or also I would say 0 as well, because 0 is on the other side of the vertical asymptote. What you really want to do is we really want to pick x's on either side of your asymptote. If you have more than one asymptote, then you want to pick an x value kind of like between each one of those vertical asymptotes. Okay, so let's see here. I'm going to do 0 first. So we'll just do f of 0. Easy calculation, right? So it should be 1 over negative 1, which is negative 1. So 0, negative 1 is one of the points right there. And then we'll try 3 here. Let's see what happens with 3. So we get, let's see here, 9 minus 6. 3 plus 1, 4. 3 minus 1 is 2. 4 over 2 is 2. Okay, so 3, 2. So 1, 2, 3. 1, 2. Ooh, and this is where I did not graph very accurately here. So let me do a different one because I think it'll be easier to see. Let me try f of 2. Let's see here. 2 squared 4 minus 2, 2 plus 1, 3 over 1. Okay, so 2, 3 is another point there. So 2, 1, 2, 3. There's that point. So this 3, 2 should be within my. Wait a minute, did I make them? 3 squared is 9. 9 minus 3 is 6 plus 1 is 7. It should be 7 over 2, not 4 over 2, Mr. Wid. So 3.5. There you go. So 1, 2, 3, 1, 2, 3 and a half. Okay. And so you can kind of like do something like that. And then I'm just going to go ahead and do something like that. Okay. So there it is. Okay. Question on any of that? Yeah. Okay. Does this graph have a relative maximum? Any relative maximums?
Yeah.
Yes, it does. Does this graph have any relative minimums?
Yes.
Yes, it does. Okay, so like if we wanted to here, we could like take the derivative of this thing. All right. Actually, you don't have to take the derivative of this. That would be a horrific mess to do that. But we could, and then see when the derivative equals 0 and figure out this point right here, right? Whatever the actual hill or valley is there. Does this graph have an absolute maximum? No. Does it have an absolute minimum? No, yeah, we do have just one relative minimum, but we also have this other part of the graph that just goes down to negative infinity. We do have this one relative maximum, but we have the rest of the graph that kind of goes off to positive infinity. So unfortunately, no absolute extrema there, but we do have some relatives. Okay. So if there are no further questions, I'll get you guys started on your assignment, all right, which will be in the book on page 191. numbers 27, 29, 63, 67, 90. Okay. So 27, 29, 63, 67, 90. Okay. What's that? Yes, you may.
Oh, you're done early.
What's that?
You're done early.
Yes, we are. I know I'm not giving their money's worth, but that means they get time to work on their homework and stuff like that.